Today we are looking at problems 20, 22, 47, and 60 from chapter 22 in the magnetism section of your book. First off, number 20 is asking, they give you the kinetic energy of a proton as it moves perpendicular to a magnetic field, and we want to know the radius of its curvature path. So first off, the kinetic energy they give you is 4.9 times 10 to the negative 16th joules, and that you can set equal to your equation for kinetic energy, which is 1/2 times the mass of a proton. Today we are looking at problems 20, 22, 47, and 60 from chapter 22 in the magnetism section of your book. First off, number 20 is asking, they give you the kinetic energy of a proton as it moves perpendicular to a magnetic field, and we want to know the radius of its curvature path. So first off, the kinetic energy they give you is 4.9 times 10 to the negative 16th joules, and that you can set equal to your equation for kinetic energy, which is 1/2 times the mass of a proton, which you can look on your pink sheet is 1.67 times 10 to the negative 27th kilograms times velocity squared, and you can get velocity to be 766,045.9 meters per second. And then once you do that, you can go ahead and use the radius equation, which is mv over the absolute value of the charge times your magnetic field, and you can plug stuff in, and the mass again is 1.67 times 10 to the negative 27th. The velocity is 7.66 times 10 to the 5th, what we got above, divided by the charge on a proton, which is 1.6 times 10 to the negative 19th coulombs, times the B field, which is 0.26, and you get an answer of about 0.03 meters as the radius of the circle there. Next one, number 22, is more of a conceptual one almost. It's asking an electron and a proton move in a circular orbit in a plane perpendicular to the magnetic field. Find the ratio of their radii of their orbits when the electron and the proton have the same momentum. So I want to compare the radius of the electron to the radius of the proton. And in the equation we just used above, the radius for the electron is going to be the mass of the electron times its velocity divided by its charge times its magnetic field, and same thing for the proton. The mass of the proton times the velocity of the proton divided by its charge times its magnetic field. And if it tells us that we know they're in the same magnetic field and they have the same absolute value of their charge, this Q times B term is the same in both, so I'm just going to cancel that out. And so what you'll get is the mass of the electron times the velocity of it is divided by the mass of the proton times its velocity. And hopefully you recognize that term m times v as being the momentum of the electron divided by the momentum of the proton. And in the problem, or part A, they told us that the two momentum, or momenti I guess, are equal, and so you'll get 1/1, and so the ratio is just 1:1 in that case. Now in part B, what they want us to find is again the ratio of the radii, but now we want to know if they have the same kinetic energy. So this one's a little bit more complicated. So we can get it down to the same kind of place we did over here, where the mass of the electron times the velocity of the electron divided by the mass of the proton times the velocity of the proton. How we're going to get to kinetic energy then is using the equation Ke is 1/2 mv squared. So that means your velocity, if I solve for velocity, is equal to 2 Ke divided by m and the square root of all that. So now, substituting that in up here above, what we'll get is, in the numerator, the mass of the electron times the square root of 2ke divided by the mass of the electron, divided by the mass of the proton, times the square root of 2ke divided by the mass of the proton. Now it's just up to the math of simplifying this. What I would do is, let's put everything under our square roots. We're going to get the mass of the electron divided by the mass of the proton times the square root of 2ke divided by the mass of the electron times the mass of the proton divided by 2ke. Hopefully you can see here that the 2ke's will cancel out, and you're left with the mass of the electron times the mass of the electron divided by the mass of the proton times the square root of mass of the proton over mass of the electron. And if I go ahead and put everything under the square root, continue down here, I will get the mass of the electron squared by putting this guy under the square root times the mass of the proton divided by the mass of the proton squared from putting that guy under the square root times the mass of the electron. And with a little simplifying, what you can get it down to is the square root of the mass of the electron divided by the mass of the proton, which, if we are ready to put in numeric values, we will go ahead and get 9.11 times 10 to the negative 31st kilograms divided by 1.67 times 10 to the negative 27th kilograms, and you get that ratio to be about 0.023 to 1, I guess, once you divide those two. So that is the ratio between the radius of the electron to the radius of the proton. Alright, the next one we have is probably the most complicated one of the set here, and that would be number 47. And what number 47 is asking is, they say you have two long straight wires that are perpendicular to the page. You have one here that is going into the page, and the current here we'll call I1 is 3 amps. And you've got another wire right here where the current is coming out of the page, we'll call that I2, with a current of 4 amps. And what they want to know is at a point P here, which is 5 centimeters from I1, and then I1 and I2 are also 5 centimeters apart. They want us to figure out what is the net magnitude and direction of the net magnetic field at point B. So we want to know what B is right there. Now, first off the bat, hopefully you will see that we are going to need some vectors, and we are going to need the distance between point P here and this I2. So I'm going to go ahead and just draw it in as a dotted line. And doing Pythagorean theorem, you can get this to be 7.07 centimeters right there. So now, first thing is, let's go ahead and find think about, I guess, just the direction at point P. So notice, if you take your right hand rule, with the current and using your thumb pointing inward at this point right here at current 1, what you'll get is that the current here is going to circulate here in a clockwise pattern. So at point P, that's right above your wire here, the magnetic field there is actually going to point straight right, and so I'm going to call that B1 in the diagram there. Now from the other from the other wire, you can see from the right hand rule, as your thumb points out, the magnetic field curls around that way, and so I'll call that B2. So at point B here, B2 is actually going to be pointing kind of down to the right at a 45-degree angle right here, and so that is going to be B2 kind of like that. So hopefully you can kind of see, if I redraw point P right here, we've got these two magnetic fields. We've got B1 pointing straight to the right, and we've got B2 pointing right here at, if I was to extend that, at an angle of 45 degrees. And so in the x direction, we're going to have a little bit of opposing magnetic fields, and so that's kind of what we have to deal with for this problem. So I'll leave that picture And now where we're at is actually going ahead and finding the magnitude. So first I'm going to find B1, the magnetic field from the first wire, and that's going to be equal to mu naught times I divided by 2 pi r. And so mu is 4 pi times 10 to the negative 7th. I1 is 3 divided by 2 pi times the distance between I1 and, or the wire, one wire and point P, which is 0.05 meters. And what you get is 1.2 times 10 to the negative 5th Tesla. And I'm going to say that's to the left, or in the negative x direction. Next thing, magnetic field B, due to wire number 2, is going to be the same equation here. So we're going to have 4 pi times 10 to the negative 7th times current 2, which is 4 amps, divided by 2 pi times that distance squared, and that's going to be that hypotenuse of the triangle right there, so 0.0707. And the result is that you get B2 to be 1.13 times 10 to the negative 5th Teslas at an angle down and to the right there, at like a 45-degree angle. So now that we have these two vectors, if you remember back to vectors, I'm going to do a little XY chart in order to break them up into components and figure out their resultant here. So I'm going to say X and Y. And first I'm going to list the magnetic fields from wire number 1, which had an X component of 1.2 times 10 to the negative 5th Teslas. And since it was pointing to the... Whoops, sorry. I totally said that was pointing to the left up here, and it should be pointing to the right, like in my picture that I had. So, since this is pointing to the right, in my chart here, I can leave this as a positive 1.2 times 10 to the negative 5th. And the Y component there was 0, so that's just going to be 0. And then from our magnetic field 2 here is going to have 2 components as well. Now notice in my picture here, it's got an X component to the left, and so that's going to be a negative component. And since your angle is going to be 45 degrees, it's going to be negative 1.13 times 10 to the negative 5th times would be the sine of 45 degrees. And then your Y component is also going to be negative because it's pointing down, so it's going to be negative 1.13 times 10 to the negative 5th times the cosine of 45 degrees. And now that we've broken them down into components, we can add our components. And what you're going to get is a positive 4 times 10 to the negative 6 Teslas in the X direction, and a negative 8 times 10 to the negative 6 Teslas in the Y direction. Finally then, if I go ahead and combine my vectors back together, I have 4 times 10 to the negative 6 in the X, and 8 times 10 to the negative 6 in the Y. And my resultant right here is going to be found using trig, and I'll just call that B. And in the end, using Pythagorean theorem, you can get B to be 8.9 times 10 to the negative 6 Teslas. And your angle, which is going to be between the two tails there, where I labeled theta, should be 63 degrees. So that would be 63 degrees south of east. So all this together will be your answer.